Now we're going to look at some of the simulation routines of SpinDynamica. So let's imagine we have a timeline and then we have a sequence of events. As I explained in the previous lecture, each of these events can be described as a pair of a generator and a duration, with the possibility of having an instantaneous event as well, described by a super operator. One specifies the initial density operator, if that's defined as time point 0, and then npropagate returns the density operator at the end of the sequence, if that's t final. So that's the task of npropagate, basically, is to take the initial density operator and propagate it through a sequence of events and return the final density operator. Now we've set up a couple of routines here which I just want to show you their functionality. One is called trajectory. Trajectory basically tracks the density operator through the sequence of events as well as just returning the final point, and lets you track, for example, what's happening to particular spin operators as you go through the sequence of events. So that's very useful, actually, for understanding how pulse sequences work in detail. And then the second routine, which I'd like to talk about, is called Signal 1D, which basically means that if you acquire a free induction decay after the event sequence has finished, in the presence of an arbitrary set of generators or relaxation superoperators or whatever, then it lets you generate that FID, which can then be Fourier transformed to generate the spectrum. So that's the task of Signal 1D. So let's see how these routines work. So I'm just going to load here SpinDynamica. And we're just going to look at this example of a composite pulse again. But this time, rather than just accessing the density operator at the end of the pulse, we're going to look at what happens during the pulse sequence itself and look at some different graphical ways of representing that. So I'm just going to use a single spin-a-half system for convenience, and again execute this command, which tells Mathematica that whenever it sees the word composite pulse, it's going to replace it by this set of instructions, which it means a pulse sequence consisting of 3 pulses with flip angles 90, 180, 90, and phases x, y, x, and using an RF amplitude corresponding to a nutation frequency of 1 kilohertz. So that's the composite pulse sequence. So I want to help you understand this. So as you can see in this example, trajectory is given 2 arguments. That's the first argument, and that's the second argument. And the first argument has the form of this rule, which is denoted by an arrow here. Actually, just to assist in that process, let me type in that command myself. So trajectory angle bracket, if I do minus and then greater than, like that, and then the second operator, Mathematica has converted that into a little arrow symbol automatically, so that's not something you need to search for on the keyboard. Okay, so let's just type that in again. The way to understand this is as follows. The first argument here on the left side of the arrow is the initial density operator. So this means start with IZ, and what's shown on the right of the arrow here means which operator do you want to follow. So this says start with IZ and follow what happens to, in this case, IZ during the composite pulse. This is easier to understand when we take an example. So let me just execute that. Now the output is not a single number or a set of numbers, it's a function. And this follows a general philosophy of Mathematica that one uses functions and objects which have functionality rather than generating numbers or sets of numbers whenever you can. So this is a function which I've called ztraj. So now this function ztraj can now be evaluated at any time point one wants. So the initial time point is 1 because we started with Z magnetization, and its initial time, its value at the initial time point of 0 is 1. If I evaluate it at, for example, 100 microseconds, it has a value of 0.81. So this is a function which may be evaluated at any time, which has been included in the trajectory. And in fact, you see in the output of the trajectory function, these numbers here indicate the initial and the final time points. So you can see the trajectory starts at 0 and terminates at 1 millisecond in this particular case. So if I evaluate it at 1 millisecond, it will give the value of -1, which is because the Z magnetization has been inverted by the composite pulse. But you can evaluate it at any time point within the range. So if you ask it for the trajectory, the value of the trajectory at 2 milliseconds, it tells you that it's out of range, so it can't evaluate at that point. So it's important then to understand that the trajectory does not return a number or a set of numbers, it returns a function, just like a sine function or a cosine function. And a function may be plotted. So here I've used another routine which I didn't mention yet, I think, which is event duration, which lets you just evaluate the duration of an event or a set of events. So rather than remembering ourselves how long this sequence of pulses is, one can use event duration just to calculate it for you. And here I've assigned the symbol big T to that duration. So I've simply evaluated the duration of the composite pulse and assigned the symbol big T to mean that duration, which in this case is 1,000th of a second or 1 millisecond. Okay, so basically ztraj, the output of trajectory here, is a function which is defined in the range 0 to 1 millisecond, which describes what happens to the Z angular momentum when the initial density operator is Iz and evolves during the composite pulse. So we can just plot it and see what happens. So what's going on there? So let's try and evaluate that. Let's just try and do a little spin dynamics ourselves. So we have, if we imagine our axis system, X, Y, Z, try and sketch in an XY plane here. So what's going on? So we start with Iz, that's the initial state. So in the trajectory calculation, I had, this was the initial state, Iz. The composite pulse involved a 90-degree pulse about the x-axis, followed by a 180-degree pulse about the y-axis, followed by a 90-degree pulse about the x-axis. So let's just figure out what's supposed to happen. The 90-degree pulse about the x-axis takes the Z magnetization down to the xy plane. So we end up with -y. So that's the first thing that happens. Then I have a 180 degree pulse about the y-axis, which, since the magnetization is now along the minus y-axis, nothing happens to it. So it just rotates around itself here. And then followed again by another 90 degree pulse about the x-axis, which now completes the rotation down to the minus z-axis. So you see that the the trajectory of z magnetization, if we plotted mz against time, during the sequence of the 90x, 180y, 90x pulse, it would initially be along the z-axis. The 90x pulse takes it down to the xy plane, so this goes down to 0 here, and then for the 180y it stays there, and then the last 90x pulse inverts, so coming down like this. And that's what we see in the plot here. So the time axis here is duration in seconds, and the y-axis is the coefficient of that particular operator that we tracked. Now, the way composite pulses work is, if, for example, the radio frequency field is a bit weaker than it should be, so in other words, when we calculate the durations of the pulses, we assume a certain RF field. But if the instrument isn't quite what we expected and the RF field is a bit weaker than we thought, then after the first rotation, the magnetization is left a bit short of the xy plane. So instead of reaching the y-axis or the minus y-axis, it's left a bit short. So this would be the case where there's an amplitude factor here. Which says that the RF field is a bit should be multiplied by this factor relative to what the pulses are calculated for. Then the magnetization will be left a bit short, though that will be the first rotation. And the trick is that the second rotation by 180 degree about the y-axis rotates the vector, which is short of the minus y-axis, round to this side. And to some degree, not perfectly, but to some degree, compensates the fact that the first pulse is left a bit short. So it takes it forward so that the second rotation now compensates the error in the first. And then the third rotation, which is also short, also subject to the same error, now compensates the error in the first rotation. So bringing the magnetization close to the minus z-axis. That compensation isn't perfect because the second rotation, which does this job, is also imperfect. But nevertheless, it can be shown that some level of compensation, and that the composite pulse has a performance which is less sensitive to this amplitude error than a single pulse. So we can simulate that as well using trajectory. So here I've used a composite pulse, but I've introduced now an option here, the amplitude factor, which is given here as 0.8, and that has the function of reducing the RF field by the corresponding factor. That's how you would calculate the effect of radio frequency field errors. So again, we calculate the trajectory. I'm just going to copy this cell and execute it again. But now for this composite pulse, which had this amplitude deviation. And then I can copy this cell and plot it. Let's just put some axes. And you sort of see what happens. The first rotation leaves the magnetization a bit short, but the second one whips it round to the other side of the xy plane and then the third rotation almost completely compensates the error in the first one. So that's an example of using trajectory. Now, trajectory has a bit more functionality. So you can track not only the trajectory of a single operator, Iz, you can track as many operators at the same time as you want. So in this case, I've asked SpinDynamica to track the trajectory of three operators, Ix, Iy, and Iz, during a composite pulse, starting from an initial density operator, Iz. And this time I get three trajectory functions, one for the x operator, one for the y operator, and one for the z operator. So I've used three different symbols here to store those trajectories. And I've called them x traj, y traj, and z traj. So at the same time, I've computed three trajectories for the x, the y, and the z. And then I can plot them all at the same time using the Mathematica plot routine. So I'm just plotting these three functions as a function of time. Big T here, if you remember, was assigned as the total duration of this sequence. So now I see what happens at the same time to the Z magnetization, which is the black one, the Y magnetization, which is the blue one. So it goes almost to minus Y, stays there for a while, and then goes back to zero again, and the X magnetization, which is the red one here. So these three trajectories, the X, the Y, the Z, they define the trajectory of the magnetization in three-dimensional space. And it's very useful to plot that in a three-dimensional graphical representation. And that's easy to do because Mathematica is well equipped with three-dimensional graphical routines. So that's done here. So this routine uses a Mathematica routine called Parametric Plot 3D, which plots a trace in three-dimensional space. And without going into the details of how to use it, basically you provide the Parametric Plot 3D routine with three functions which define the x, the y, and the z positions of the points, which should depend on a parameter, in this case time, which runs between two values. So this is perfectly equipped to plot the output of the trajectory routine. And in addition, there's a sphere and axes routine, which is part of SpinDynamica, just to give an attractive plot which resembles the sort of literature things you have. And here we see the trajectory of the magnetization in 3D space, and one can visualize how the magnetization is first rotated by almost 90 degrees about the x-axis. Would be exactly 90 degrees if it wasn't for that amplitude factor being 0.8, but falls short, and then the y rotation by the central pulse takes the magnetization around the y-axis. If that 180 was ideal, it would go to an exact mirror image position, but that also falls short. But nevertheless, it's in a better position with respect to the third rotation than it would be if you just did a single pulse. So that is a way of visualizing how this simple composite pulse works. And one can plot such trajectories for any operator under any sequence of events, starting from any density operator. Let's see another example here, a spin echo sequence. And I show this to introduce another important piece of functionality. So again, we have a single spin-a-half system. And here's another trajectory command. So what is this? So let's look at the pulse sequence here. The pulse sequence, the sequence of events used here involves, first of all, a delay. Actually, the only purpose of that delay is just so that the plot is a bit easier to interpret, because the the start of the sequence doesn't coincide completely with the left edge of the plot. So that's just for visual convenience to have a little delay first. And then a pulse 90 degrees about the x-axis. So if we start with Z magnetization, that is used to excite transverse magnetization. Then a delay of duration, in this case 0.6 seconds. And then a 180 degree pulse about the y-axis. And then another delay. So that's basically a 90 delay, 180, another delay sequence. So a spin echo with a little bit added on in the front and a little bit added on in the back. Now we want to simulate that in the presence of a resonance offset. So I've used a background generator here of 7 Hertz, 2π7, multiplied by the Z operator. So that gives you a resonance offset. And then we can plot the trajectory. So what are we seeing here? So initially nothing happens, and that's because I had this initial delay of 0.1 seconds. And then there's a sudden change in the magnetization because of this, in this case, an infinitely short 90 degree pulse, which generates minus Y magnetization, which is why we go from 0 to -1 here. And then we have precession. So now the magnetization rotates around the Z-axis at this 7 Hertz frequency. And it keeps rotating. There's no relaxation in this simulation. We could add that later. It keeps rotating, and then eventually the 180 degree pulse hits. And that's where you get this discontinuity. And now the magnetization continues to rotate, and so on. And we can use we could track the X, the Y, Z trajectories and then do the same as we did with the composite pulse. So that would be true. That would be possible. Now, a spin echo is all about refocusing magnetic field inhomogeneity. So to simulate that, I don't really want to simulate just a single resonance offset, in this case 7 Hertz. I will want to simulate several different resonance offsets in order to simulate the effect of a spread in magnetic fields. So for example, if I do the same simulation again, this is exactly the same, but now with 4.5 Hertz resonance offset, I get a slightly different picture. But again, you see the step which happens when the 180 degree pulse arrives. And I could repeat those simulations for many different resonance offsets and add them together to simulate a spin echo. But how would one do that properly? Let's just imagine. So suppose we have an NMR spectrum, and I suppose it has a certain width. Not because of intrinsic relaxation in the system, but because the sample has a spread of magnetic fields. The magnet is not completely homogeneous, or maybe it's a complex material which has different regions in it, different susceptibilities, and so on. So actually in here we have a whole set of spin packets with different resonance offsets. So let's suppose that the reference frequency of the spectrometer is here, and suppose the peak we're interested in is 10 Hertz off resonance, but suppose it has a width of 5 Hertz. Because of magnetic field inhomogeneity. Now in statistics, you would say that there's a distribution, a statistical distribution of resonance offsets here. And in the absence of any other evidence, you would probably guess that it might be a normal distribution. So a bell-shaped curve, a Gaussian, with a certain center point at 10 Hertz, and then a standard deviation of a half of 5 Hertz. So to simulate that in a decent way, what one would like to do is to sample a distribution and generate an ensemble of simulations in which one specifies the probability distribution of a parameter, in this case the resonance offset, and then take a set of samples from it. Now it turns out that Mathematica provides a large body of routines for generating distribution functions, statistical distribution functions of essentially arbitrary complexity, and then sampling them. And this is an example here, has been used here. So what this line here, this is Mathematica, this is not SpinDynamica. But what this line here is saying, take a normal distribution with centered at 10 Hertz in this case, with a standard deviation of 5 Hertz, and take 100 random samples from that distribution. So if we just execute that, then Mathematica now generates a set of random numbers, but the probability distribution of those numbers is sampled from a normal distribution. So they're not evenly spread across a certain range. Their probability is determined by this Gaussian function. So that's 100 samples. And for example, we can use Mathematica to show the histogram of how those samples are actually distributed. So we see that there's only 100 of them, so it's not a great picture, but as generated, they're centered at approximately 10 Hertz and with this certain width. If we do that again, then we probably get a slightly different pattern just because these are random. And if we take 1,000, then we probably get a better representation of the Gaussian distribution. Okay, so now we have, here we've sampled 1,000. Let me just I'll go back to 100, so simulation doesn't take too long. We've sampled 100 different frequencies, but distributed according to this probability distribution, which has been defined by this single line of code here. And one can also in Mathematica define one's own statistical distributions and then sample them. And correlated distributions with several variables are also possible, and so on. So how do we now perform simulations averaged over such a distribution? So there's a very powerful routine in SpinDynamica. All of the simulation routines are equipped with an ensemble average function, which works as follows. So we've defined our pulse sequence, and we've defined, in this case, a background generator, which depends on a variable. In this case, here we leave it symbolic. So we say it's a resonance offset, and let's give it the symbol big omega. And then to average that variable, all one needs to do is specify a definition for ensemble average that variable, big omega, now takes a range of values which we specify. And in this case, Mathematica supplies those values by sampling a normal distribution. So we can just execute that. It's giving a little information on setting up the computation. But now it's generated a trajectory, but now this is an average trajectory for all of those 100 different simulations for magnetic fields, 100 different magnetic fields chosen from a Gaussian distribution. And what you see now is the spin echo. So you see what happened. The 90-degree pulse excited minus y magnetization, but that rapidly dephased because of the magnetization vectors spread out, because each one is experiencing a different magnetic field. So essentially the free induction decay is rapidly quenched, but returns. So somewhere in here is the 180-degree pulse, and then that generates an echo. So all the magnetization vectors have been flipped over by the 180-degree pulse and now reconverged to make a spin echo. So here you see an example of simulating a spin echo. If we used 1,000 different samples for the magnetic field, actually SpinDynamica will divide the computation up into batches. It says here that it's computing with 8 batches. The number of batches can be controlled and so on. It's giving some messages about combining the trajectories together. There's a little progress bar there. As you can see, it takes some time. In general, by default, SpinDynamica distributes such calculations over several kernels, meaning computational engines of Mathematica. So it does parallel computation on all of the kernels which are available to the Mathematica session. So if Mathematica is set up on a supercomputer which has access to 1K kernels, license for 1K kernels, then it then distributes the computations in parallel over those kernels without you having to do any intervention in that behalf. In this case, on a laptop, it's using 4 kernels. So the 1,000 ensemble members here have been divided into groups of 250, with each kernel handling 250 of them. And you can see now the spin echo is a little bit more accurately defined. So this is very general. One can specify in trajectory or the other relevant routines an ensemble average over any symbolic parameter with any distribution, which may also be weighted. And in fact, you can even do it over several different, more than 2 or 3 or 4 or 5 parameters, specifying the distributions of each of them. But I won't cover that more complex syntax now. So this could be used, for example, in solid-state NMR, where you need to do an averaging over powder angles. It can be used as here, in simulating the effect of an inhomogeneous magnetic field. It can be used in imaging to specify computations over many different voxels in the presence of field gradients, and so on. So it's a thoroughly general functionality. So now let's move on to another computational routine, signal 1D. And this is every NMR spectroscopist wants to know what the spectrum looks like. So this provides the one-dimensional spectrum at this particular point. Although one can simulate 2D spectra by writing some code oneself, at the moment there's no general-purpose signal 2D routine. That will hopefully evolve in the future. So let's just see an example of it, just to illustrate how it's used. In this case, I'm going to use a 2-spin-1/2 system. And I define a Hamiltonian which involves I1Z multiplied by 30 Hertz, I2Z multiplied by minus 20 Hertz, so chemical shift difference of 50 Hertz, and a J coupling of 10 Hertz in its full form of I1 dot I2. So this is a scalar coupling in a homonuclear spin system. So what we're simulating here is going to be an A-B pattern for a strongly coupled spin pair, as a simple example. So signal 1D calculates the free induction decay in the presence of a Hamiltonian, for example, by specifying the background generator, just as in the other routines. And it needs little information as to how to sample the free induction decay. And actually there are a number of different ways of specifying that syntax. The one I've chosen here is probably, I find it the most convenient, is one specifies the spectral bandwidth, in this case 100 Hertz, 2 pi times 100, and specify that 1K points 1024 1K points should be sampled. There's other syntaxes where you can specify the time interval of the sampling points and so on. But I usually find this one the most convenient, and that's indicated by these double curly brackets. So this execution then simply simulates that spectrum for that particular Hamiltonian, which of course could be anything. And you get the result is not a set of numbers, but a signal object. In fact, the output here shows some things about it. The first piece of information here tells you the time range, so going from time 0 up in this case to 10.22 seconds with a step of 10 milliseconds. That apparently corresponds to these parameters I used here of 100 hertz bandwidth with 1K points, and contains 4 Lorentzian peaks. And to plot it, so this is a free induction decay. To plot it, we can plot the real part of it using the mathematical list plot routine. Looks like that, just like you expect an NMR signal to look like. And we can also Fourier transform of it using the FT routine of SpinDynamica, and then plot the real part of that. And we get the characteristic 4-peak pattern of an AB system. So that's straightforward, I think, and you can have any spin system and have any Hamiltonian, including physically unrealistic ones with strange couplings between 3 spins and so on. Now, to get the full functionality of signal 1D, though, you need to use its many options. So let's have a look at some of them. If all routines, actually, both in Mathematica and in SpinDynamica, have a large number of options. These are the things which you specify using these rules with the arrows. And the way it works is if you don't specify anything, then it uses defaults. So you can examine the defaults by this type of syntax. If we just look at the options for signal 1D, here one sees all the possible things you can tell signal 1D to do. You can specify which operator basis it's going to use, which Hilbert space basis it's going to use, what the initial density operator should be, what the preparation should be, and what to observe, and so on. If you're interested in knowing what the default is for a particular option, you can use this syntax. So this is saying preparation is an option for signal 1D. What's its default if I don't specify anything explicitly? The default for signal 1D is a rotation superoperator involving all of the spins with a corresponding to a 90-degree pulse about the x-axis. So what this means is if signal 1D is not told anything different, it will assume that the first thing you do to the spin system is apply a 90-degree pulse about the x-axis. So again, if here I'm just defining the Hamiltonian again, and that was already done. Again, so when we execute, so this routine now, it's all in a chain now. This means execute signal 1D with these particular sampling parameters in the presence of this background generator, the Hamiltonian, take the Fourier transform, take the real part and plot it. And we can chain everything together so it does it all in one line. And this would be using the default for preparation, which is just a single 90-degree pulse about the x-axis. But we can override such defaults by specifying it explicitly. So here, the preparation has been specified explicitly not to be a 90-degree pulse about the x-axis, but to be a 90-degree pulse about the y-axis. And of course, the output now is 90 degrees out of phase, a dispersion signal. And that preparation can be any event sequence. So to calculate the spectrum generated by a complicated pulse sequence, that might be a long pulse sequence object itself. And so the signal 1D routine will first of all deploy npropagate, which I just talked about earlier, to calculate the density operator at the end of the preparation sequence, and then use that in the signal 1D routine. In this case, the preparation has been defined as a pulse sequence which contains a 90 about the x-axis, and now a delay of 10 milliseconds in this case. The background generator still acts during this preparation, so that will cause some precession under the resonance offsets and the J couplings in this case as well. So we expect to get some phase shifts in the signal due to that initial evolution. So that's the way you can specify the pulse sequence which was applied before the FID was calculated. Another option is the initial density operator. So we can examine what the default is for the initial density operator. And in this case, the default is just the Z operator. So just assuming thermal equilibrium along with the magnetic field along the Z-axis, and using this slightly non-rigorous but functional density operator just proportional to IZ. And again, we can override that if we want. So in this case, the initial density operator has been specified as minus IZ, and we get an inverted signal. Another very simple default. As you've seen, the free induction decay here decays, not because we've implemented relaxation here. We can do that, and that will be done in the next session. But at the moment, this decay is just an arbitrary numerical damping of the signal, just to give an attractive spectrum which doesn't have truncation artifacts in it. The default for the line broadening, that's this decay function, is automatic, which in Mathematica generally parameters are often specified as being automatic when an internal algorithm is used just to derive what's a suitable value. In this case, SpinDynamica chooses a value which causes the free induction decay to decay to 1% by the end of the free induction decay, just in order to get an attractive result without too much operator intervention. But again, you can, of course, specify what that is. So here, line broadening of 2 Hertz has been specified, so we get broader signals. And that broadening can be applied at the time of Fourier transform rather than inside the signal 1D routine. So there's no need to actually repeat the calculation, but here it's been done that way. And then again, we have ensemble average, in which we can take a particular parameter in the Hamiltonian or the relaxation superoperator and generate many computations, if we want, sampled from some distribution function. In this example here, so I'm executing signal 1D here with a given background generator, that's the Hamiltonian, which defines the couplings and chemical shifts in the spin system. And I've left the J coupling here symbolic, because that then allows me to specify an ensemble average for the J coupling. And actually here I've simply said 2 values of the J coupling, one of 10 Hertz, one of 20 Hertz. So in this case the ensemble is just 2 calculations. And I get a signal which now contains 8 Lorentzian peaks. Let me just edit my notebook here. I'm just going to add the Fourier transform and the plot in that. And now, of course, we now have 2 AB systems with 2 different values of the J coupling. So that was a simple example. And here I've chosen a more complicated example, where again, I've said just arbitrarily, suppose the J coupling, for some reason to do with the molecular structure, has a distribution. And I've assumed here it's a normal distribution centered at 10 Hertz with a spread of 5 Hertz, and I'm going to sample 2,000 values from it. So SpinDynamica will now perform 2,000 computations. Again, it's divided it up into batches. It's distributed the computations over the 4 processors available in the laptop here. It takes a little time now. And it will give some probably rather ugly spectrum in which the spectrum is broadened by the fact that the J coupling in this model has some random distribution. I have no idea if that corresponds to a physical realizable system or not, but clearly you can define these sorts of distributions and different parameters according to the type of variation or inhomogeneity in the system one has. And one now generates a spectrum which has been broadened, in this case, by distribution of J couplings. If we wanted to say instead, suppose we wanted to say instead that the chemical shift of spin number 1 was distributed. The chemical shift of spin number 2 was still fixed at minus 20 Hertz in the rotating frame, and the J coupling was fixed to 10 Hertz. Then that's the syntax one would use there. So the background generator is a Hamiltonian where the chemical shift of spin number 1 has been made symbolic. So it can now be sampled from a random distribution. I've used 2 pi here to make sure that the Hertz gets converted to radians per second, which is needed in the Hamiltonian. So let's see what happens when we execute that one. So again, it has to divide up in the 2,000 computations here into 16 batches. And the task is distributed over the 4 kernels accessible to the Mathematica running on this laptop. And we expect, I guess, we'll see what happens, but I expect that the one side of the spectrum, which belongs to spin number 1, will become broad, and the other side belonging to spin number 2 will remain narrow. But it might not be as simple as that because the spins are strongly coupled. So let's see. Right, so there you go. So this is the spin number 2 side. Remains rather narrow. And the spin number 1 side, which was given distribution of chemical shifts, is now broadened. So this ensemble average facility is very powerful, actually, for understanding how complex systems behave. Final argument of signal 1D is the observable option. So usage message accessed by the question mark. The observable used by signal 1D is in general an operator, and you can specify any operator. But you can also specify, instead of specifying an operator, you can just specify which spin you want to observe. So you can use either of those functions. If you look at its default value, its default is all, which means observe all of the spins in the system that you've defined. But in heteronuclear systems, you might very often want to say, well, actually, I just want to look at the protons. I don't want to get an FID from the protons and the carbon at the same time. That generates a messy spectrum. So for heteronuclear systems, so here I've defined a Hamiltonian for a heteronuclear system. There's a product, the J coupling now is just a product of the 2 Z operators, appropriate for a heteronuclear system. And if we generate the signal using signal 1D, if we transform it, take the real part, plot it, we get 2 doublets because we're observing, SpinDynamica doesn't know that you only want to observe one of the 2 spins. So it's actually generated a composite spectrum, which is the sum of the proton spectrum and the carbon-13 spectrum, if that's what the spins are. So to specify that you only want one of the spins, in this case spin number 1, then you just use this observable argument. And then you only get the spectrum of the spins number 1 in this case, and if we used spin number 2, we presumably get the other doublet. So I think that gives you an overview without going into all the details and without showing all of the functionality of these routines. But it gives you an idea of how trajectory and signal 1D may be used to perform simulations.